linear classification model with the so-called perceptual models. So in the perceptual models, and we say we have a model here that we want to build a decision boundary based on linear combinations of the input features. And however, the perceptual learning algorithm, we didn't provide you a loss function, right? And how do you train it? We just simply provide you an algorithm. So the learning algorithm, and it has a strong motivation. And we mentioned that this perceptual learning algorithm is very similar to the online gradient descent applied to linear regression models. So it's kind of, the update rule is a product between the residual, which is the difference between prediction and the target values, and times this so-called sensitivity variable. And in that case, it will be the input X. So the product between the two. So within the perception learning algorithm, we do this online learning. We update the parameters whenever we see one example, one training example, and then we'll update the parameter right away. So the perception learning algorithm was proposed a long time ago. It has some advantage in the sense that this algorithm is guaranteed to converge after a finite number of steps. So this is kind of important, after a finite number of steps. And so this is in some way is different from the behavior of the gradient descent type of algorithm. In gradient descent algorithm, that there's no guarantee whatsoever say the algorithm will converge after finite number of steps. The only thing we are saying that the algorithm will converge, will approach asymptotically to the optimal solutions. But that can, in order to reach that optimal solution, that will run infinite amount of time. So the reason because the gradient descent algorithm is trying to optimize objective function, but the perception algorithm, we actually do not have objective function. So even though we have something in mind, that's the accuracy, we want to reduce error rate. And that's something loosely speaking, but the error rate itself, so that loss function is not differentiable. So we cannot calculate gradient based on the error function itself. So instead, we need to do something else. So, so today I'm going to talk about this gradient-based classification learning. So that's what we talked about. We started talking about last time. But I like to kind of, instead of look at the slides, let's revisit what we talked about so far. So I like to kind of start from the scratch. Hopefully, that'll give you a better understanding of the things we talk about now. So, so in the context of consider the linear regression, linear classification. So we'll say we're going to start with data. So let's see what is our data here. And data here is consisted of xi and yi, pairs of x and y. And then we have I goes from 1 to m. We have m sets of that. So the collections of these pairs is our training data sets. And then the xi here is in general is n-dimensional here. And the yi here is a binary variable. So we're going to start talking about binary classification. But today we should have opportunity to generalize to arbitrary multi-class classification, but we're going to start talking about binary classification. So in that case, so target value is going to be either two values. So for now, we're going to choose 0 and 1. So you can choose to be +1, -1. So that's another choice. But for now, we're going to use this notations of 0 or 1 to annotate these target values of the y. And I kind of mentioned last time here, in fact, in real applications here, we need to think about how do you represent this input variable, x, represent the features. So in particular, if your data is kind of a categorical, how do you represent them? And we talked about something kind of 1 out of k representation, essentially one categorical variable of k different values. We actually represent them with a k-dimensional vector. So that's kind of more general representations of the categorical value, something you need to think about in the real applications. But for now, we already sorted this out here. We have clear representations of data. So next thing what we want to do is we want to come up with our models here. And that's the model here right now we consider something relatively simple is linear models. Essentially give me x here. I go through my model here. And this model here is a linear model, essentially calculate linear combinations of the input with some weight parameter, coefficients correspond to each individual features. So we get something called, and let's say I call it the score here. So that is a theta dot x here. So this will be a response or score. Score S is a linear combination of the input here. If you want to write down specifically, it will be theta 1 times x1, theta 2 times x2, and so on. Theta n times xn. So by using this notation here, I just want to remind you again, there's no bias term in this linear response. The reason for that is because we already augmented the input features. So within the x here, the first component will be a constant 1. So we're going to make that assumption. So with that assumption, the response was simply the inner product between theta and x. Theta is our parameters here. Theta is the parameter. Here's the parameter. So overall, so we're going to have a n parameters that we need to learn from the data set here. So this is our model. And then the decision here. So decision is typically is saying if the score is greater than certain threshold numbers. For instance, I choose them to be 0. If the 0, we say predict target label is 1. Otherwise, predict target label is -1, is 0. Is 0 here. So or predict is 0 here. I want to say, and then I will say this is 0. So this is the perceptual learning algorithm. What do we talk about here? So in general, that is this: with a higher score, we'll likely assign the score to label 1, otherwise label 0. So I just want to again remind you here, the exact value of 0, 1 does not really matter here. It's just a number associated with this individual class. And you can decide the other way. Say if x greater than 0, I assign target value to be 0. Otherwise, assign target value to be 1. That's okay too. And then the parameter you learn in this way will be slightly different, will be opposite signs of that. But as long as you make it consistent, and then there should be no problem with that. Right. So this is a decision process here. So the question in this case here is how to learn the parameters of the model. And so in terms of and then next thing we talk about is this loss function here. So question, what is the loss function? So in the loss function, one immediate loss function is the error rate. So error rate is essentially percentage of the samples that you classified wrong. And however, this error rate model here is so essentially is over m, summation of j goes from m here, the indicator function saying that your predicted value of j sample is not equal to the actual ones here. And that's the error rate model. So fortunately, error rate is not differentiable. So as a result of that, I cannot directly optimize the loss function using some efficient methodology. So theoretically speaking, I can still write down, say, I'm going to minimize the error rate with respect to parameter theta. And that you can write down that type of model, optimization models. The only challenging in this case is we do not have an efficient methodology to solve this problem. And because most of the optimization algorithm is based on some information by calculating the gradient of the loss function with respect to parameters. If you cannot calculate that, usually it is hard to solve the optimization problem. So that part is kind of difficult to do. So you said, what we talked about last time, we introduced one kind of a loss function is similar to the MSE we talked about on the linear regression models. The only difference is this. For this now, we're going to kind of squeeze this response score here to let it bound it. Because right now the score S can be and goes from -infinity to positive infinity because just linear response of the input here. So it depends on your theta that can be very large or very small. It's unbounded. However, my target value is either 0 or 1. So I like to make it comparable. So the way we did it is to introduce a function and something called a logistic function. So this logistic function is the functions of sigma of z. So let's first talk about here. So this function is in this mathematically is in this way, e to minus z power of z, and then take the inverse of that. If you try to plot this function, it will look something like this. So this is z, this is sigma here. If you want to plot them, you'll see that the function is bounded between 0 and 1. And then When z is 0, that's 1/2. And then otherwise, we'll take this form here. We'll try to approach 1 on the right-hand side, approaching 0 on the left side here. And this is the so-called sigmoid function. So we'll approach 0 and 1, but we'll never reach that value. So only kind of asymptotically approach that. So which means that, so that when z is very large, it's kind of approaching the 1, so that because our target value is 1 is somewhat comparable. When z is very negative and approaches 0 and not somewhat consistent with our target value of 0. So it's making it more comparable. And then what we did, and it was formula this loss function using this logistic function. So let's talk about loss for one sample. For one sample saying this, if you give me x and y, so y, remember now, is a value of either 0 or 1. So we use this to annotate labels. And then what do we go with this? We'll give x here, we have a score, theta dot x here. So theta x here, and then I'm going to apply this sigmoid function on the scores. So essentially, we're going to squash the score such that make it between 0 and 1. So we do not care about the, we do not want to be very large, as long as it's very positive. I said that's reach a bound of 1. If it's very negative, we'll reach the bound of 0. So make it between 0 and 1. So, so we're going to compare these guys here with this actual observations. And want to make sure this overall difference is small. So it's something like an MSE. So, so you can imagine, you can think about that. In this case here, our model here is this. You can think about another way to think about it. This is a new model. You have x here, goes through the linear response. So the first of all, goes through the linear response here. You get something to be theta dot x here, right? So that will be new variable. And then what do you do here? You go through a nonlinear transformation here. So that would be sigmoid. Logistic. And then you produce a targeted value y hat. So now you can think about y hat now, your predicted value is here. It's not a binary values, but it's a continuous number between 0 and 1. So I can write down, say, in this framework query, I can interpret this, say, I'm going to predict this my target value to be sigma theta dot x here. So now I'm going to treat this as my predicted value. So this is going to be a number between 0 and 1. So between 0 and 1 here. And I want to, so what I want to do is this, I want to make this y hat as close to y, the target value, as close as possible by minimizing the MSE difference between them. So that is part of the reason this type of binary classification, in many cases, sometimes is, you can think about it, it's something like a regression problem, right? Because now I try to regress the difference. The only difference now is this, I have a new kind of surrogated loss functions here. And that is to be treat this y hat as my predicted values of that. And then once you have these guys here, well, the overall loss function, the L here, of the parameter theta here, I just need to average this individual sample loss across all these training examples I have. And that will be M here, logistic function theta dot, the J samples of that, and then minus the labels, these guys, and take squares. And that's kind of a simple versions that you can construct a loss function and based on MSE loss. So this logistic function sometimes is called a sigmoid function. So there's different names for that. If somebody says I'm going to have sigmoid function, that means this is this function here. All right, so now once I have loss function here, the learning is formulated as the minimize this loss function, right? This big loss function here with respect to all combinations of the theta. And then learning is formulated as an optimization problem. If we know how to solve this problem, and then we'll be able to identify the optimal parameter theta. And then of course, in this class here, we emphasize a lot about this algorithm based on gradient descent algorithm. So in the gradient descent algorithm here, the key part is going to update the parameter iteratively. And the key step of that is to calculate gradient of the loss function with respect to the parameters. So if I know how to calculate this quantity, and then I will be able to update my parameters. And for now, let's think about it here. So let's think about the gradient of each individual sample loss with respect to theta. If I know how to do that, and later on I'll be able to average the gradient calculated across all samples. So which means let's calculate the loss here with respect to for one sample. So which means I want to calculate a gradient of these functions here, and sigma theta dot x here minus y, take square of that. And how to calculate the gradient of this guys here. Well, so I can simply apply the chain rule from the calculus. So in order to calculate the chain rule saying this, right? If you want to calculate the derivative of this function here, but this function is fx here, but then and you have another function to be outer loop of this function here, it will be g of fx here. And the question, you might have something even outside that, maybe say f5 here. And you have multiple loops of that. And how do you calculate gradient of this function with respect to x? Well, the chain rule saying this, well, first calculate gradient of f here. So that would be g fx here, evaluated at this point here. And next, I'm going to calculate the derivative of g function, evaluated at fx here. And the next, I calculate the derivative of f function, evaluated at x. So you can apply this repeatedly. And essentially, that's what you learn from your calculus. And once you're familiar with this rule here, the chain rule here, you can apply to this formula. First, if I treat this quadratic function, that will be the phi here. The next, we have a linear function. The next, I have the sigmoid function and a linear function. Again, you can apply this repeatedly. So as a result, you have 2 here. That will be result of quadratic function here, minus y. So it will be linear term. Once you x squared, derivative x squared is 2x. And the next, I'm going to apply to the sigmoid function here, derivative sigmoid, evaluate theta x here. Remember that's theta dot here. And next will be calculate the gradient of the theta dot x with respect to theta, and that's x here. Okay. And that's the gradient of this loss function here. And in order to calculate this guy here, I know everything here. This guy here is this is the predicted values, target predicted values minus these actual observations here, and they have coefficient 2 in front of that. And then they have this guy's here. This guy's here, essentially, what is the gradient of this sigmoid function? And essentially, what's the gradient of this guy's here? If you carry out this kind of derivative calculation, consider inverse function, and they have this exponential function, you realize that it actually have a relatively simple form equal to sigma z times 1 minus sigma z here. So it look like this form. So this gradient here, essentially the slope of this curves here. The gradient here will be 0 because the slope here is 0. And then the gradient on this side here will be 0 as well because slope is 0. And however, the gradient here, you have certain values of that. In fact, here is 1. So essentially, gradient will go from 0 and then increases and then decreases. And in the end, it decreases again. So gradient would take this type of forms of that. Closer to 0, and then increase to be a 1 here, and then decreases with 0 here. With something like that. And in fact, then you can calculate based on this guy. So this is gradient of the logistic function. And once you know the gradient, you just plug in here, calculate this quantity. But in the end, the bottom line is this, right? So you have this gradient here is some number between 0 and 1, just scalar values. And this term is important. So this term is the residual, the difference between prediction and the observation. And this is a major signal that you use to guide training your model parameters, because it depends on y hat minus y is positive or negative, you're going to change the directions of the theta differently. So that's the most important part. And then the sigma transpose here is the sensitivity parameter associated with the x here, right? And then you have x here. X here is the sensitivity parameters here because your gradient gradient impact of parameter theta on the loss function will depend on x. If x is positive, so if you increase the theta, so that will lead to increase of your predicted values. So on the other hand, if your x is negative, if you increase theta, will actually reduce your score. So you can see the impact of theta on the scores depends on sign of x. So that's really it's important to put in here. So that's the sensitivity parameter. Well, so the bottom line is once you do that, you know how to calculate the gradient here, and then you're going to average this gradient with respect to all the parameters. And in the end, we will have an update rule for updating these parameters here. So you know how to learn those parameters based on this MSE loss function here. So, so this is what we talked about last time here. So today, what I'm going to do here, I'm going to introduce a new type of loss function here. So this loss function here is based on a new motivation. So in this motivation here is this. So when we talk about the base classifier in the previous lectures, and we talked about how to calculate the posterior probability of labels given the x. So this is a base classifier here. So in that case, what do we care about is that we want to calculate this quantity here. We want to calculate what's the probability of y given the 1 here, given your input data x here. We like to calculate this quantity. And however, in the context of the base classifier, and what do we talk about this? Oh, well, in order to do this, we say the first step, we need to calculate the prior distributions of y here. And prior distributions y equal to 0, y equal to 1. So this is a prior distribution, prior probability. And then next say we want to model this conditional probability. And this is the probability of the x given y equal to 0, probability x given y equal to 1. So we want to model these two guys. And then, however, you know, when we talk about here, that becomes a little bit tricky part because in how do you model multi-dimensional distributions of x values? And in that case, what we say, what depends on the, you know, the overall distributions of x, and then the model could be different. And all depends on whether x is continuous and discrete, and we have to treat them separately. And so, however, we say, well, if you make this assumption, saying that if x is a continuous quantity, and if they follow the normal distributions, and then you can use multivariable normal distributions to model the distributions of these conditional probabilities. And then if you do that, if you remember that, recall what we did last time. We say, well, so in that case, if you do that, in that case, the posterior probability of the p y equal to 1 conditional x here, and then would depend on something like this, would be 1 over 1 plus exponential of this log ratio scores here. You know, there's something here, z here. And z now is to be the log ratio between probability, conditional probability of y equal to 1 divided by log, let's do this one here. To be the log of ratios, y probability of x here, given y equal to 0, and divided by probability of x given y equal to 1. And that's what we talked about last time. So now, and then we say, if, you know, if the data, if both models are modeled by the Gaussian distribution with the same covariance match, share the same covariance match, but with different mean. One is mu0 and mu1. If you make this assumption, it's saying that, well, if you make, we need to make assumption saying that these two conditional distribution, and it can be modeled by a normal distribution with the same covariance structure, only with different mean vectors. Only the center are different, the covariance structure is the same. So in that case, we say that this guy is here, the log ratio between these two, in fact, becomes a linear function, if you remember that. And this guy here becomes something like this, theta dot x here, linear combinations of the parameters, and plus a constant term, plus a bias term here, right? Plus theta 0, a bias term here. And that's what we talked about last time. So what this means, right? The means is this: the probability of this guy here is now can be written down as this: probability of a target label to be 1 conditional x here is equal to, again, remember this is actually a sigmoid function here. Sigmoid of the score here. If you absorb this constant into this vector, into the augmented feature x here, this becomes theta dot x. If you absorb theta into this augmented feature here. So now it's interesting. If you look at this guy here, now it has more interesting meaning. Well, with certain parameters here. So parameter theta here depends on mu 0 and mu 1, but combine them, right? It's combined of mu 0 and mu 1. In fact, if you remember the formula, it's going to be the difference between mu 0 and mu 1, and then transformed by the covariance matrix. So, but in the end, it will depend on some parameter theta here. The theta here summarize the effect of the theta 0 and theta 1, right? So, but however, in the end, if you look back here, if you think, well, what this tells you this, essentially, if I wanted to make this assumption here, essentially the posterior probabilities here can be modeled as a sigmoid function, right? Sigmoid function, and then with this z here to be simply the score, the linear combinations of the input with some parameters, coefficient parameter theta. And that's what this means in these models. Okay, so let's go back here. Let's summarize what we talked about here. What do we talk about here is this. So in fact, if you are willing to make some assumptions, and then in the end, this posterior probability of y equal to 1 given x here is equal to this 1 over e plus e minus theta dot x. Okay, so that's what we talk about, dot x here. Essentially, this is a sigmoid functions of theta dot x. And that's what we talked about so far. Under the assumptions of this kind of a constant variance structure, and also the normal distributions of the conditional distribution of x. And this is how these things came from historically. It is motivated by this kind of a probabilistic interpretations. However, you can go beyond that. You can say, well, maybe I don't need to make the assumption. I will just start with this model here. Just simply start with this model. I want to say this. Well, I'm going to model my prediction. So my prediction in the end is going to be y hat here. So we're going to say this is going to be coming with new models here. In this model here is theta here goes through linear response. So linear response to get a score to be theta dot x here. And next I go through as a new sigmoid functions here. And to get this y hat. So y hat is the same thing as we talked about before. Y hat is simply same as what we mentioned in the previous slides here. However, now I have interpretations of this y hat. So y hat now, the interpretation is equal to the probability of assign label 1 to this input x. So this kind of interpretation is very powerful because you can do a lot of interesting things. Once you say, well, this guy's here, in fact, is this probability of assign label y equal to 1 given x. Well, what this means, immediately, you will know what is the probability of y equal to 0 given x here. Well, it's simply 1 over y hat. So that's the probability of that. All right, so now you get two things here. Essentially, you know what is the, you know these two quantities here. One is the probability of y equal to 1 is equal to y hat. And then next is, in the probability of y equal to 0 given the x here is this 1 minus y hat. And that is the posterior probability of assigning labels to different classes given that particular input. And this information is in fact very useful because it not only simply try to assign a label, but tells you more information. Essentially, it tells you, what is the confidence level if you assign this to be 1 here. And if y hat equal to 0.9, and that means you are very confident. I will be very confident assigning label 1 to this sample here because the probability of y1 is 90% versus 10% for assigning label to be 0. So most likely I will willing to assign 1 to that sample. On the other hand, if your y hat equal to y hat here equal to 0.51 here, okay, suppose that's the case. So in this case, what the probability of assigning y equal to 1 is 51% versus 49% for assigning label 0 to the sample here. Essentially, they are more or less equally likely. There's not much difference between two. A slight bias, but more or less equally likely. And in that case, you know that in that case, essentially, I don't have enough knowledge to put labels on these data sets because both labels are equally likely. So this is different from perceptual algorithm because perceptual algorithm is saying this, well, I have to put a threshold here. I'm going to assign 1 to these data sets here. Anyway, because that's my algorithm was doing that. Algorithm itself cannot tell you how confident is this assignment. But this model here will be able to do that. And because of that, it's much more powerful. All right. So once we have these guys here, and then we can come up with formulate some loss function for this models here. So the way we formulate loss function here, we're using something called a likelihood calculation from the statistics. So in statistics, we're saying this, we'll call this guy here, and the probability, suppose now you're given x and y equal to 1 here, y equal to 1. So given a sample here, so now your x here, let's say given a sample of x and y, given a particular sample. So now the model predict this, model predict that y hat equal to this guys here, sigma theta dot x here. So model is willing to make a prediction. Just keep in mind that y hat is the probability y equal to 1 Bmax. So that's what this y hat means. So now given here, this is a model prediction. Now let's see how is this guys here compared to the actual annotation, the actual target value y here. So now let's look at two possibilities here. So what happens if y equal to 1? So which means this data here is x and labeled with 1. So now you predict that the probability y equal to 1 is y hat, what we talk about here. And essentially, look at it here, right? Depends on this values here. So if this value is small, suppose this value is equal to 0.1 here. And then you know that this model is not doing very well because you predict this guys here to have a very small probability here. And in fact, this model would tend to give higher probability to y equal to 0. So essentially you have opposite predictions here. So that's not good. And on the other hand, if I say my y hat here is equal to 0.9, and then what you say that your model is doing pretty well because you are predicting the assign higher probability to the actual labels here, and that's good. So for these reasons here, and if y equal to 1, the higher the values, higher this guys here, the better, right? The higher the better. And this guys here is something called likelihood. What's the likelihood of assign my data to exactly this observation here? That's called likelihood. And then the higher the likelihood, the better is the model. So similarly, in other case, if your actual observation is 0, and what is the likelihood of seeing label 0? Well, for that purpose here, I need to calculate the probability of y equal to 0 given x here. And that is 1 minus y hat. And that's your likelihood. corresponding your labels to be y equal to 0. So that's also likelihood. So you can see the likelihood calculation here depends on the true observations, depend on true observation. If your true observation is this guy here, and then this will be your likelihood. If your true observation is 0, and this will be your likelihood. So they are different, right? So the likelihood here is not necessarily confidence. The likelihood just say how consistent is your model compared to your actual observations here. And the higher likelihood, the better. So that's the two cases here I talked about here, right? And this is remember, keep in mind, y is your targeted values. It's true observation, it's true values here. And this is your model predictions here. If y equal to 1, if true value is 0, I want to say what's the likelihood of my model predict exactly the target here. And that's y hat. The higher the better, right? If y hat is equal to 0.9, that's good. So on the other hand, if the actual observation is the actual level is 0, then if your y hat is 0.9, and that's a poor model, poor likelihood, because you're more likely to assign y to be 1, although in reality y is 0. The reason because the likelihood would be calculate the probability of y equal to 0. So that we're going to calculate the probability of the actual label scale, and that's the likelihood calculation. So likelihood depends on the actual observations, right? So this likelihood. But in general, what you can do, you can optimize your parameters to improve the likelihood, because the higher, the better. So that's just your brain, think about it this way. The higher, the better. All right, so we're getting closer. So we're gonna do one more trick here, is this. So that typically, the likelihood is not easier to manipulate. Instead, in this community here, people like to do something called log likelihood. So log likelihood is saying, well, I have a likelihood here. This will be a number, right? This will be a number given that particular sample. I will be calculate. If it's a 1, this is y hat will be my likelihood. If your actual target is 0, 1 minus hat will be my likelihood. So in general, people put a transform this here by apply a log function. And in that case, I'll get a log likelihood, and that will be log of y hat. So in one case, it will be log of y hat. So that's one case. The second case, it will be log of 1 minus y hat in the second case. All right, that's something called a log likelihood. Remember, the log function is a monotonically increasing function. So it's still good. The higher the log likelihood, the better the model is. So it doesn't change the direction. That's good. And however, if I want to convert this into something like a loss function, so that's something we have to be careful now, because in the loss function, we're trying to minimize it. So the smaller the loss, the better. But however, the log likelihood is opposite. So the higher, the better. So how do we reconcile the difference? Well, the way we do that, we put a negative sign in front of that. So we can just say, okay, we can say negative in front of this guy here, and I call this guy here called negative log likelihood. Okay, so and this will be my negative log likelihood. And so let's summarize what I talked about so far now. Okay, so the way we are saying this, let's talk about negative log likelihood. This is my loss function. And the loss function. And this is saying this. So giving a sample, x and y, a pairs of them. So y has certain values, either 0 or 1. And then the loss here, formulated as a negative log likelihood, is equal to log of y hat if your target value is 1, or equal to negative log of 1 minus y hat if your target value is 0. So that's what I talked about so far. Right. So let's look at this, if you agree with me so far. So depending on your target values here, if you use 1, the negative log likely is minus log of y hat. Y hat is my prediction here. The model prediction is this. Is y hat equal to sigmoid of theta dot x here. And then we have the interpretation of y hat. This is the probability of y equal to 1 given the x here. And that's why we talk about it. All right, so this is my new loss function. And what I'm going to do here is I'm trying to optimize my select my parameter theta to minimize this negative log likelihood. And and that's what I'm going to do here. Well, sometimes people write down this instead of using this if-else terms here. And sometimes people write down this negative log likelihood using one sentence, and that's what I'm going to do here. And they're equivalent, just a simplification in terms of notation. So I'm going to write down this here, say y times log of y hat, and minus 1 minus y times log of 1 minus y hat. So it's more or less like a symmetric here. Y times y log y hat, and then plus minus 1 minus y times log y hat here. So negative sign in front of that. You can also think about this way, is plus here, and then this guy here. And you can think, so you can see this notation here is equivalent to this guy here. Well, why this is the case? Well, I'm going to verify that. So because y here is binary, y is either 0 or 1. It's different from y hat. Y is a continuous number, but y itself is binary, either 0 and 1. So if y is 1, and this terms disappear because 1 minus y is 0. So only this terms exist. So that will be same as this guy's here. On the other hand, if y is 0, and this term disappears, and then 1 minus y is 1, so only this term survives. So that is the same as this guy's here. You can see they are equivalent, but people tend to like this notation here because it is more compact. I do not need to write down the if terms within the functions of that. Well, so now I have the loss associated with the 1 samples. And now what is the loss associated with all samples? And that will be the overall loss function here. So this will be my parameter function parameter theta here. I'm going to average across all the samples here. All right. So now, and I'm going to write down that negative here. I can put negative here, put negative in front of here. So I don't need to write it again. And then within that will be y here, the j sample of that, and times log of y, predict j samples of that. And then plus minus 1 minus y of j labels of the j samples here, and then log 1 minus predicted probability of the j samples, and then put them together. And this will be my loss function. And this loss function overall is called a negative log likelihood motivated loss function. It sometimes is also called a binary cross entropy. So that's another terminology used very often, but they means the same thing. And that means the loss function I just wrote down here. Okay. So and in this case here, y hat, the prediction here is sigmoid functions of theta dot this j sample of the input. And that's these guys here. And if you know this guy, you can plug in, calculate this loss function here. All right. So once I have the loss function, what I can do here, well, I can optimize this loss function, because this function here is going to be actually a smooth functions of the parameters here. And there's no threshold function involved in these terms here, because it's going to be a sigmoid of something. Sigmoid itself is a smooth function. So overall, it's going to be a smooth function. And as a result of that, I can calculate the gradient of this function here. So the next will be learning. So learning here, and identify the parameter here to minimize the loss function, cross entropy or negative log like functions here. And for that purpose, I'm going to apply the gradient descent algorithm. And then for the purpose of that, you're going to calculate the gradient. So that's, again, come back again, how do we calculate the gradient of the loss function here with respect to the parameter? And how do you calculate this quantity? So now this is slightly more complicated than the MSE function, what we talked about before, because here you have, sounds like complicated, because you have this log here, and then y hat itself is the sigmoid of this input score here. And then the question how to do that. Right? So now I'm going to write, I'm going to first calculate gradient with respect to one sample loss. And then once you do that, you can calculate gradient over all samples by taking average of that. So we can do this. Let's calculate this over one loss here. One sample loss with respect to parameter. Essentially, it's going to be gradient of theta of this terms here, right? Minus y here, and then will be log of theta dot, sorry, let me go back here. Log of sigmoid theta dot x. So that's the one term. The next term is 1 minus y log of 1 minus sigma theta dot x. And that's it. And this is for one sample. This will be gradient calculation with respect to theta. So it looks like it's slightly complicated here, but you can carry out these individual terms here using the chain rule I talked about here, right? Let's say, well, let's first calculate these terms here, minus y gradient of this log theta with respect to theta. And how do you do that? Well, first take the log function here. That will be theta dot x here. And now we 1 over that. And the next will be the gradient of the theta function. And then times gradient x. So that's the first term. And then you can consider the next term, right? So I don't want to, you can complete that. And I just want to show you that that's not hard. You just need to be careful enough to go over this carefully and write down the terms then. And then now I'm gonna tell you one trick here. One trick is this. You remember that the gradient of the sigmoid function is what? Sigmoid of theta dot x here is equal to sigmoid of theta dot x times 1 minus sigmoid of theta times x, if you remember that. Well, so what this means, now this guy's here, cancel this guy's here. And then, so in fact, you do not have the issues of something appearing in the denominators that, because otherwise make your life harder. In fact, the only issue remains here, if you do this guy's here, the terms remain here will be minus y, and then next will be 1 minus sigma theta dot x times x here. So that will be the first part. The second part is simply, it's very simple, but I don't want to write it down. I just want to encourage you to go over it yourself, and you can see that. So in the end, if you do that, the final result is this. The final result is this. It's going to be y hat minus y times x here, as simple as this. So that's the gradient of one sample loss with respect to parameter theta. And if you look at it here, it's exactly the same in format, as the gradient of the linear regression models. So in linear regression, we say is difference between your prediction and the observation, and then times the sensitivity vector x here, the input vector x. And here is the same. And the only difference here, the interpretation of the y hat is different. So in the previous, in the linear regression, y hat is simply theta dot x. Under this new models here, y hat is sigmoid functions of theta dot x here. And of course, y is different as well. Previously in linear regression, y is a continuous number. Here is a binary number here. But however, it has striking similarity here. This is something called residual. This is the error models here. And I mentioned that depends on whether this is how big is this residual here, what lead to different ways to change the gradient. And this is a sensitivity parameter. And in the end, the formula is very simple and you can memorize. It's simply say, well, loss is simply, again, exactly the same as linear regression. Is difference is a product between residual and the input x. All right, so now this is a loss for one sample, but now I can calculate the loss for all the samples I have. And now we go back here, the gradient of loss function, overall loss function with respect to theta here, and that will be average across all the samples I have. And with these samples here, I can now simply calculate the residual of j samples minus the actual observations of the j samples here, and then times the xj input here. And that's it. And that's the gradient as simple as this, to be the gradient of this negative log likelihood function with respect to parameters. So in a very striking and simple form. So, and then you can update your parameter delta theta, choosing to be the negative of the gradient here. And then you update theta to be theta plus alpha times the gradient of j with respect to theta. And you updated this iteratively here by choosing a learning rate alpha here. And that's what I'm going to do until learning the parameter of this model here. And the model I talk about here is under using this negative log likelihood as loss function is something called logistic regression. And that's the name used in this community. It's a misnomer here. It said logistic regression, but it's not a regression. It's a classification problem. So that just I don't know why people use this terminology, but and just keep in mind when people mention something and say I'm going to apply logistic regression to solve a classification problem, what they mean is to use the negative log likelihood as the loss function and the train parameter, learn parameter this way. And that's the logistic regression models. All right, a couple of things I want to mention here. So first of all, I'd like to mention here is, so this loss function here, you look at this one here, it looks complicated. Right? Looks complicated. However, it's actually very similar. It's almost similar in some way to the MSE loss as in linear regression. So, however, there are some difference here. The difference here in this case here, the gradient here, and if you set gradient equals 0, and then you have an equation, but you cannot solve the equation analytically, as in the case of the linear regression, because in that case you can't derive a normal equation. And if you solve that system linear equation, you derive a solution. But for linear regression, you do not have analytical solutions. You have to use iterative methodology, something like a gradient descent to identify the parameter. So that's one thing here. So has to use iterative methods, no analytical solutions. No closed form solutions. Right. Have to use the iterative method. So we have to, right? So in this case, unlike in the case of linear regression, you might argue, well, I could use the method of solving system linear equation to derive solution. But here you do not have that. So that's one main thing mentioned. And the other thing you mentioned here is, I mentioned that this type of gradient descent methodology is sensitive to the initializations. Depends on how do you initialize the parameters here. The solution might be different. So this is a generic statement regarding the gradient descent algorithm. And however, and we mentioned that depends on the shape of your loss function. If your loss function look like this type of shape here, and then you see that there are multiple values, and then there's an issue, and then we call that this locally optimal solutions. Local. And then we say that gradient descent will be happily end up with any one of the locally optimal solutions. And that's the limitations of the gradient descent algorithm because only equipped to identify this locally optimal solutions. And however, we mentioned previously in the case of linear regression, we say the MSE loss function is not, it's a quadratic function. It's actually look in this type of shape here. And this type of shape is something called a convex. And the convex means there is a strict, more rigorous definition of the convex. But more or less saying this: if you draw any dots here, try to draw a line between these any two dots here. And that line is always above the graph of the function itself. And if that's the case, that function is called convex. You can see that's the case. But this is not the case, right? If I draw a dot here, you can see the line is actually, line segment actually appeared below the graph itself. And this is not convex. And this is a convex here. And because this is the case here. And there are many functions that are convex. For instance, the negative log function is convex, right? So so the log function, this is negative, this is the negative log function, is actually convex. There are many forms, not in quadratic function is convex, but some quadratic function is convex, but there are other functions that is so-called convex. The convex function is interesting, and because convex function does not have this kind of multiple local values, local minimals, and you can prove that. If you have a function here that is convex, and you can show that, prove that there's no locally optimal solution. Any solution you found that is locally optimal is also guaranteed to be globally optimal as well. And for this reason, the convex function is great, because you know that if you apply gradient descending algorithm, it will always end up with a globally optimal solution, no matter how do you initialize it. And put another way of saying this, different initialization will end up with the same solutions. And it is not sensitive to the initialization. And the MSE is good because the quadratic loss function, MSE function, is a convex function. So which means if you apply gradient descending algorithm, will tend to end up with the same solutions here, no matter where do you initialize it. So the question is, what about this function here? The cross entropy negative log likelihood function. It turns out, you can show it. I will not show it here. It turned out this function is a convex function as well. So that's a very interesting, very powerful observation. So because of this reason here, because it is a convex function, and then which means the gradient descending algorithm here is actually guaranteed to discover globally optimal solutions. So that's a very powerful statement. It's saying this, gradient descent will lead to globally optimal solution. So that is a very good property, because you do not need to worry about initialization anymore. So you randomly initialize, as long as it can converge to optimal solution, and you are sure that that is the solution I'm looking for. And this depends on how do you initialize. So that is fantastic property. In general, for most of the problem we talk about in machine learning, it does not have these properties. But for logistic regression, if you are using this type of loss function, it does have these properties, because that is very attractive. All right, so this is so-called logistic regression. If you apply that, you can discover the solution to the problem here. All right, let's look at it. Let's revisit what we talked about. And so far, let me show you some of the slides I have here. So I'll skip some of the slides. You can go over them, more or less talk about the same thing I talked about here. So So we talk about different types of error functions, loss functions so far, to formulate the problem. So this comes back to the topics I kind of mentioned at the very beginning. This type of loss function is actually essential. It's very important part of this machine learning algorithm development stages. That a different choice of loss functions sometimes will lead to very different results. So don't underestimate that. And then you can see from here. Essentially, we talk about three types of loss function here. One is the error rate function. Is fractions of the predictions here are incorrect. This is called error rate. And this is more or less, this is something the perceptual algorithm is trying to minimize, trying to reduce the error rate, and because the perceptual algorithm only cares about this guys here. And then, however, we say that this function here, it's not differentiable, and because of that, it's very hard to develop an optimization algorithm to minimize. Essentially, it's very hard to do. And next, we talk about this logistic MSE loss function here. We construct a logistic function and then take a square difference between the predicted values and the observation here. This is more or less like MSE. Essentially, this loss function looks like this, right? Suppose your y is 1 here. Suppose your true observation is 1. Now you look along this axis here. This is a score function here. You think about this. And this saying this, if score is less than, if S is a positive score, and that's good, because positive, and most likely after thresholding, you're gonna assign positive label to this data set. So they're consistent. So the MSE loss was saying, I'm gonna use a relatively small loss here. That's good, because they are in the right prediction here. The model should not be imposed any loss here, so that's good. The interesting part is this side here. And look at this side here. And this side says, if your actual observation is 1, however, your score is actually very negative in this case. And which means your model is doing poorly because you predict something is opposite. And within this logistic MSE loss, you're going to impose this loss function here. Essentially, because look at the difference between sigmoid and the y here, and then we'll increase, and if you're more negative, but however, we'll saturate here. Their saturating point here is because sigmoid function is a saturating function. And which means that no matter how negative you are, the loss here is bounded above. So that is the result of the logistic MSE. So now if you look at this negative log likelihood here, so negative log likelihood behave differently. So again, so this is a score here, and when score is positive, and what you are seeing is this, the loss will decrease gradually, well approaching 0 when S is very positive. So that's good, which means that if score is positive, and then there's no loss. However, there will be a loss here. Even score is positive. The loss, just like in both cases, will not be 0. Essentially saying, even if you are predicted correctly, even if you are separate these two data sets correctly now, the model still penalizes you. It's saying that you're not separated large enough, separate those two group points large enough. And therefore, you ask you keep learning. So that's this algorithm is doing. That's one observation. Another observation is this, on the negative side here, on this side here, what you notice is this. So the negative likelihood will become unbounded going upwards here. In fact, you are seeing later on become linear, going this way, linear here. And this means the more negative you have here, essentially the more opposite direction you are going, I'm going to put more loss on this function. And that's actually is a desired property, saying that the more negative you have, you're going more way off to the, in terms of prediction, I'm going to put a higher loss on your models here. So because this reason here, I think this is better than this logistic MSE because this is simply bounded up with a fixed value there. So after a certain negative value, you don't care anymore. But this model will say, and I'm going to penalize more because you're doing even worse. All right, so that's really, there's a motivation for that. So this is so-called negative log likelihood. So negative likelihood, just keep in mind that loss is this linear here and then decays gradually. It's continuous version. That's something you keep in mind here. Linear on the negative side and then decays gradually on the positive side. And then this guy here, even if your score is positive, it still imposes a loss, which means you need to push your score on the above that side here. Don't stay around zeros. And that's because these reasons here, if you look at this, and one example we mentioned previously. So one example, we talked previously, this example here. And we talked about this this training data sets here in 2 dimensions here. And this data set is a linearly separable. And this is one solution here. This is another solution on the right-hand side of that. In the first solution here, and then the error rate is 0. In both cases, the error rate is 0. However, you can see now, the negative likelihood of saying that this loss function of this guy, of this model here, is going to be higher than the loss on the right-hand side. The reason is this, because the score here, they are positive. They're slightly positive, but they're close to zero. And I remember that for the MSE loss, sorry, for the negative likelihood loss, so even if you are negative here, there's still non-zero loss you're going to impose on the function then. So the function was trying to say, stay away from the regions close to zeros. And that's what it was doing on the right-hand side here. You can see there's no dots surrounding the decision boundary here. And the decision boundary will around the regions that score near zero, and it will push away. And as a result of that, you can see, I will imagine this will generalize better because there are clear separation of boundaries between these two group points here. Later on, if there's some new data sets, I will imagine this will do better. And hence, this is great. You can see when we optimize, try to develop a learning algorithm here, it's not trying to simply optimize the accuracy of the models here, but need something more, and in order to get good performance of that. All right, so that's what